So, well, it's a pleasure to be here. And I have the topic. I didn't realize it was going to be a circle packing conference when Bob invited me to talk. But so it's may sound a little off topic, but there is some part of it which is all about circles or co-circularity and cross ratios. So sort of kind of the idea of the proof. The sort of co-circularity is going to drive the proof, although not the topic. So the plan is I'm first going to describe what this thing is, the farpoint map, and then I'm going to talk about a special kind of map of the plane called a rhombus, which I call a rhombus map. I'll say the main theorem, sketch some ideas in the proof, and then I'll talk about some of the, well, maybe more of the ideas of the proof or what drives the argument. So, and then here's a link. I just finished writing a paper on this. It's on the archive, and that's the number for it. So there it is again. So the farthest point map, you could do this game on any compact metric space. You just pick a point, and then you want to know what's the farthest point from that point. So here I've given two examples on the disk. The x is on the boundary, then f of x is the antipodal point. It may not be a single point. Like in this example, if you start at 0 and you just are on the triangle, then 1 is the farthest point, and then these 2 points that the other vertices are both in the far. It's really a map from a point to a set of points, but often it's unique, and you can try to do dynamics if the map is frequently unique. So that's the map I'm going to talk about. There's some literature on this. My friend Peter Doyle got me interested in this. So I'm going to talk about it on a polyhedron with the intrinsic metric. So that means you measure distances on the polyhedron by lengths of paths. If you use the chordal extrinsic metric from R3, it's pretty boring. You just immediately move to a vertex, and then you're stuck at a vertex. You move around the vertices. So the chordal, the intrinsic metric is much more interesting. And so Rier worked out the exact picture for the tetrahedron, and a student at Cambridge, actually, when I gave a talk about this, about the octahedron, Yuri Tumarkin worked out what happens for all tetrahedra. Then there are some general results. There have also been some results about general convex surfaces, and it's closely related to questions about the cut locus of a surface. So I worked out what happened for the octahedron, and so you might wonder what happens for the platonic solids. What does this map do? The cube. This must be worked out somewhere, but I don't know where. But I worked it out, and it's sort of like the octahedron. My graduate student, Zili Wang, wrote a paper about centrally symmetric octahedra where all the cone angles are equal. And then the icosahedron is similar to the octahedron. Today I'm going to talk about the dodecahedron, which is the most complicated and the most beautiful of the platonic solids. So the plan is to tell you what the farthest point map does on the dodecahedron and why. And actually, you'll be maybe a little bit disappointed. I can't really tell you why. All I know is a computer-assisted proof. I mean, it's a rigorous computer-assisted proof, but you'll see why. I hope I also will make clear why you really would need to do a computer-assisted proof for an analysis of this thing. Okay, so one thing I want to say is that the regular dodecahedron is centrally symmetric. If x is in it, so is minus x. So it's better to look at the farthest point map and then apply the antipodal map, because then you're kind of not moving very far away. So rather than look at the farthest point map, I'm going to look at I'll call it the anti-far point map, which is the composition of the antipodal map and the far point map. And the maps commute, so you can do them in either order. For the circle, it's the identity. So you can see it's a little bit nicer. You might guess for the Platonic solids that the map is the identity, but it turns out not that this anti-far point map is the identity, but it's not. It's some other thing. So now maybe before the next slide, I'll just talk. Like, you could ask yourself, like, what are the simplest two-dimensional maps? And probably everybody would agree that like translations are the simplest things you could do to the plane. And then maybe next, isometries. Then maybe similarities would be next. And then affine transformations. And then something popular here, conformal transformations of the plane or real projective transformations. Those are sort of all the kind of nice things you could do. And then you might ask, what comes next? Like, what's the next simplest thing you could do after a projective transformation or a conformal transformation? And so I'm going to describe a map, which is sort of like the next thing up. And I'm going to call it a rhombus map. So the input to the construction is a rhombus. I mean, you could do this for any quadrilateral, but I'm just going to talk about rhombuses. And you give a rhombus and a vertex and an edge. And here's the construction. You pick a point Z, and then you draw a straight line from the vertex to Z, and you intersect with the diagonal. This gives you this point Z prime. And then you draw this other line until you reach the red line L, which is parallel to the edge. And this is your final point, is what I'm calling REV of Z. So this is some kind of map of the rhombus. And I'm really only going to think about it in these two domains. And the map generally, it preserves the foliation by lines parallel to the edge. And when you restrict it to each line, red line, it's a projective transformation or a Mobius transformation, and it fixes both endpoints. So this map tends to sort of push points away from the bottom and towards the top. And it's sort of like, you could call it fibered Mobius. And this is a weird way to describe it. I mean, you could just compute an example. And so if you take the square of side length 2 that's centered at the origin, and your V is -1, 1, and your E is this vertical edge, then this is the formula for the map. So it preserves all the vertical edges, the ones parallel to E, and then that's your holding X constant. And then it just looks like X squared plus Y over 1 plus I. So when restricted to each vertical line, it's a Mobius transformation, and it has its fixed points on the boundary of this pink region. It pushes everything up, and then all the other maps for any other rhombus, they're just equal to a conjugate of this by a similarity. So if you know this one, you sort of know the dynamical behavior of all of them. So that's what a rhombus map is, and I guess I would describe it. It's a birational map that's just sort of a step up from a Mobius or a conformal or a projective transformation, step up in complexity. So now we're going to get to the dodecahedron. So what is a dodecahedron? It's the Platonic solid with pentagonal faces. And to understand this map, you really only need to understand what happens on one face, because, on the other faces, it's just the symmetric picture. So the first thing I'm going to do is describe a decomposition of a face into 15 regions that I call states. And the construction, these blue lines are supposed to indicate the construction. You first draw the sort of pentagram in the pentagon, and then you make this inner pentagon, and then you draw these other lines. And anyway, this gives you some kind of decomposition into the a face of the dodecahedron into 15 regions, which I call states. And I call them states because they're going to have smaller regions, which I call cities. And so this is, each state has 4 edges, and there's 15 of them. So that's all I wanted to say so far. I might as well just say something qualitative first. It turns out that the omega limit set of the far point map is exactly the boundary of these states. So in other words, if you just pick a generic point inside and you start iterating the map, it'll converge to the boundary of this tiling. And so that's sort of a corollary of my theorem, that there's this tiling of the regular dodecahedron by 180 convex quadrilaterals, and the omega limit set of the anti-far point map is the one skeleton of that tiling. So that's you could think of that as being a corollary of the result. So now I'm going to start. Okay, so I'm already building up towards the theorem, but let's put these together. There's 40 rhombus maps that I'm going to associate to the regular pentagon, just the pentagon in the middle. And so here in the middle is this black pentagon is like supposed to be one face of the dodecahedron. And then I've got these much larger rhombuses, which are sitting outside of it. And I've also drawn some scaffolding of other pentagons, which describe, these tell you geometrically how to construct these larger rhombuses. And another way to say, like, both of these rhombuses, these are the rhombuses that appear in the Penrose tiling. That's what their shape is. And for example, like this one, its diagonal has 3 times the length of this diagonal of the pentagon, and this one has some other lengths. But anyway, these are 2 of 40 maps that I'm going to associate to the regular pentagon. The other 38 are just obtained from this by dihedral symmetry. So you can either apply a symmetry of the pentagon and you'll get 20 that way, or you can switch the flag to the opposite one. So that amounts to replacing the map by its inverse. And here, what I've drawn in the center of this picture is one of these states. This darkly shaded quadrilateral here is one of the 15 states. And this red edge is kind of selected by the map. It's on the diagonal of the rhombus, and it's contained in the omega limit set of the map. So if I were to iterate this map, I'd go to this red edge. And this is also in the case here. If I iterate the map, everything would go to the red edge. So I've just described for you 2 of 40 maps, and the other ones are just rotated and reflected images of these. And each map selects a unique state edge pair. So sort of to each edge of each state, there's a unique map. And now I can tell you the theorem with the picture. Each state is divided into 4 cities. And here you can see I've drawn with yellow outlines 2 of the states, and I'm showing you the 4 cities inside of them. And in each city, the map is one of these 40 rhombus maps. And which one is it? It's the one that selects the outer edge of the city. So that's the main theorem. It's an exact description of the map. This picture maybe doesn't quite do it justice. So I'm going to show you what it looks like when you can move around and draw the far point map. So here, I made this program. Really, I made the program first and then wrote the paper based on what it shows. So here if you zoom out, here's the rhombus map. And so in here, where my cursor is, that's the point P. And then this point over here is AF of P. So, and so you can see, and then the map is defined by this rhombus, which is a little bit too large to see. And then kind of curiously, when you cross over to here, to the other region, the map actually varies continuously, but the rhombus changes. So it's sort of a continuous change, but it's not algebraic or even differentiable. And then when you cross from the blue to the red, the map is replaced by its inverse. So on this blue-red interface, the map it's the only place where it's not one-to-one. There's 2 points that are equally far away, and then the map switches. So then you can do the dynamics. You can just push the button, and you see the map going. This is what happens when you iterate the map, and it converges to this point. If you start over here, it goes the other way. So this is a little demonstration of why the omega limit set of the map, namely the accumulation set of the orbits, is the one skeleton of this tiling. The thing that I was really impressed by was that if you look at this curve, this red-blue interface, you might guess that it's just the obvious straight line that connects the midpoints. But in fact, it's not. And it's not even a piecewise straight line. It's given by algebraic curves. And maybe I'll bring this up. See if I can do this. Let's see. So this little piece here, this is its equation. It's some cubic curve where the coefficients are these big numbers in this finite degree field extension of Q. Now, you can also get a formula for like this vertex. This vertex, the x coordinate satisfies this irreducible degree 10 polynomial. And it has a non-solvable Galois group. And the y coordinate, the x coordinate satisfies this one. The y coordinate satisfies this degree 20 polynomial. It's really a degree 10 polynomial on y squared. It's also non-solvable. And, so somehow these triple points, the places where the farthest point where these three kind of piecewise domains for the far point map meet, it's a totally canonical point associated to the regular dodecahedron. But then the coordinates of the point have non-solvable coordinates, and they satisfy this polynomial. I didn't actually prove that they satisfy this polynomial, but I checked it, in Mathematica and Sage up to 10,000 decimal places. So, I'm pretty sure. So anyway, this program does a lot of things, and I'm going to return to it. But the rest of the talk is really just to explain to you how you prove this. That's the answer. And I'll just maybe show you one more thing. You can see these rhombus maps sort of moving around as you go through. So that's the answer. And now I'll tell you the proof, or just the ideas and the proof. And again, be warned. I mean, I won't actually give you a proof. It'll be more like a strategy for a proof. And okay, so the first idea in the proof is that the farthest point of any point is on the opposite face. That's not obvious. Yep. Question. Is there? So the first step is to show this, that the farthest point map is on the opposite face. And let me tell you something crazy about the regular dodecahedron. If you look at distance minimizing paths from a point on one face to a point on the opposite face, this path interacts with the other faces. It goes through them in some combinatorial pattern. And there's actually 70 different patterns that are realized. So already it's like a really complicated thing, like just getting from the bottom to the top, there's 70 ways to do it. So, you have to sort of eliminate these things, or first you have to enumerate them. Anyway, the first step is this, and I'll talk a little bit about this first, and then the next step I want to describe intuitively. So there's this thing on the regular dodecahedron or any other, convex surface like this called the cut locus. And it's what it is you pick a point on the surface, and then the cut locus for nearby points, you can access them by unique distance minimizing geodesics. But the cut locus is like the closure of the region. It's all the points that are not accessed by unique distance minimizing geodesics. There's more than one distance minimizing geodesic joining the point to that point. And for things like polyhedra, the cut locus is some kind of a graph. And I want to convince you that the farthest point has got to be a vertex of this graph, because imagine you're just in a region that's accessed by a unique distance minimizing geodesic. Well, that's not going to be the farthest point because you can just push it a little bit further away. And now imagine you're on the edge of the cut locus. So you can be accessed by two distance minimizing geodesics. Well, there's still, like, I'm making a little V with my hands. There's still a direction you can push that will make things go farther away. So you really need three different distance minimizing geodesics coming in together at the farthest point. And the directions have to be they can't lie in the same half space. So this step 2 is sort of, rather than working with the cut locus, I just want to work in the plane. And so there's a certain hexagon I'll construct, which kind of, and then I'm going to take the Voronoi decomposition of the hexagon, which is, what that means is the Voronoi, the cell for each vertex is just the points closest to one vertex than to any other. And then the edges of the Voronoi decomposition are kind of a proxy for the cut locus. So the idea is that once I know that the thing is on the opposite face, I argue that there's this hexagon, and then the farthest point map is just amongst the vertices of the hexagon. And then the final step is just a kind of a competition. Like, you have a point and then you've got some candidate vertices and you want to know which one is farthest. And for any given point, you can compute this by hand or on a computer, but you want some argument which is going to work for all the points. And this amounts to proving things like structural stability for the cut locus. In other words, as you move the point around, you don't want the combinatorics of the cut locus to change. And when do they change? They change when an edge shrinks to a point. And that happens when 4 of the vertices become co-circular. And then you measure that by the imaginary part of the cross ratio vanishing. So ultimately, the way I prove everything is that I express all the things I want to prove as statements about various cross ratios having positive imaginary part. And then I apply some kind of algebraic positivity criterion to these various functions I get. There's something like 500 functions, and I just kind of go through them and work them out. So that's sort of the general, those are the steps in the proof. now I'm going to go into a little bit more detail in each of these things. And so the first thing I want to talk about is, why is the farthest point on the opposite face? So I'm going to give a kind of a proof by pictures. So firstly, it's not going to be on a neighboring face. Like that's pretty clear. Like the distance between a point on the bottom face and a point on the neighboring face it's less than something like the semi-perimeter of the inscribed sphere of the dodecahedron. So in other words, the distance from a point to its antipodal point is further than the distance from a point to a neighbor. Anyway, it's not on the neighboring faces. They're obviously, those aren't the farthest points away, but then it's a real pain to talk about why couldn't it be on the faces that are adjacent to the bottom face. And so to study this problem, I'm going to look at the developing map. So what I'm showing you here is just a kind of a scheme for the dodecahedron. It's not like in Oleg's talk. It's just a kind of a plan. And what you want to do is the distance minimizing geodesics on this are locally straight lines. And I'm going to start in face 0, and I'm going to move. I'm really going to go into face 9, because face 9 is adjacent to the antipodal face, which you can't see. And this is a very handy coloring to use when studying the developing map. There's a beautiful 5 coloring of the vertices of the dodecahedron, which has the property that the vertices of the same color are the vertices of a regular tetrahedron. So I'm going to use this nice coloring to sort of keep track of what things look like. So you might ask yourself, like, how many combinatorial ways can you get to the point 9, which aren't ridiculously long? So like maybe you would look at things, you have to basically, sorry, that's the wrong program. So I'm going to show you this thing. So just give me a second to set this up. So this is one way. This is like the most straightforward way to get from 0 to 9. This is the developing image of some geodesic. And here would just be a straight line segment that connects some point in the gray one to some point in the green. And here's another way. You could sort of go like this. And here's another way. And here's some more ways. So basically, I did a computer search and I found all the ways. This window has some other ones. This one, for example, you can go here and you can actually go to the top and then come back around. So there's a bunch of these other ones too, and they seem worse somehow, but how do you rule them out? So now I'm going to take you through the proof. Why can't the farthest point be in face 9? So here's what I'm going to do. I'm going to talk about what I call the Magenta Variation. So I have a point in the 0 face, and I have a point in the 9 face. And if I just push the point directly away from the magenta vertex, I go farther away from my point, because the perpendicular bisector, this pink line, it separates the green from the gray. So when I push away, I go farther away. So if I happen to have this combinatorial type of path to the supposed farthest point, I can just push away. And that also works for this one. Again, if this is the combinatorial type, I can push away. And likewise for this one, and this one, and this one. Oops. This one isn't quite good. In this one, the pink line cuts through the gray. And so if I'm over here, if I have missed, this one doesn't have this property. If I can do the magenta variation and it fails. However, what saves you is that there's no point between the blue and the magenta, which you can draw to the gray, which has this combinatorial type. So you're really out here, and then you can still do it. So anyway, there's a few where you have to scramble, but all of these are the good ones. If your distance minimizing path has one of these combinatorial types, then the magenta variation will make you far away. And so if all of your distance minimizing paths have just these types, then one and the same variation pushes you further away. But what about these losers on the left? Like, they don't have this property. They're really bad. Like, here the magenta variation is awful. It just moves you closer. So the next step is I really have to show that none of these other guys could be the combinatorial type associated to a distance minimizing path. So I'm just going to explain the idea for one of them. What I do is I find what I call a bottleneck. So this quadrilateral here, this aqua quadrilateral, any path from the 0 to 9, from the gray to the green, it's got to go through this quadrilateral. But then the same quadrilateral is over here. And so if I have some path through the quadrilateral over here, it's going to start like a little bit outside the quadrilateral and go a little bit outside the quadrilateral. But then there's a shorter path over here that starts in the same places. So I can do a little surgery operation and I can find a shorter path on this other combinatorial type. So this is the existence of a quadrilateral like this and another one that's sort of the same size but better situated allows me to prove that this guy is just not a distance minimizer. And then there's a few where you see exactly the same quadrilaterals. And then there's some where they're not the same, but the one on the right is smaller. So if I have any path on the right, I can transplant it to something shorter on the left. Yeah. Anyway, the idea and the proof is that you do a computer search and you find all plausible combinatorial types that go from the bottom face to face 9. And then some of them, there's this good variation you can do, and the rest of them, you just prove geometrically that they're not distance minimizing. And there are just all these different types. My program will it'll plot exactly which pairs of points correspond to actually realized paths. And anyway, so this, I don't want to talk too much about this part. This doesn't have anything to do with the cross ratio. This is just to get you to the opposite side. Okay, so let me go back to the outline. You could summarize step 1 by saying that kind of a computer search plus cut and paste arguments get this result. Okay, so now I want to talk about this result about the vertices of a Voronoi decomposition of a certain hexagon. And I want to show you the hexagon first, let me show you the hexagon, and then I'll get to the proof. So firstly, there's a decagon. Now, what is this decagon? What I'm doing is I'm taking the central pentagon and I'm developing it out. And these different paths are the 10 most straightforward ways to get from the one face to its opposite face. So you might guess that any distance minimizing path from this face to this face is given by one of these, but these are 10 of 70. And so the main idea is to sort of show that in the cases I care about, I only have to worry about these 10. So let me show you the decagon. So, well, firstly, the coloring out here is special. It's the only way to color the outside in a way that's dihedrally symmetric. And these colors are like the images of, if you just color the opposite face using the antipodal coloring, this is what it looks like when you develop it out along these paths. So what I can do is I can pick a point in the center and I can draw a point out here in the same location. So here in the center, this point is very close to the pink and the green. And then the vertices out here are very close to the pink and the green. And so I have this decagon, and then I take its cut locus, its Voronoi decomposition, and then this essentially, what I'm really doing is I'm taking the cut locus and I'm looking at its image under the antipodal map. But then, rather than look at the decagon, there's actually, in each one of these regions, there's actually a hexagon, which has the same local picture. So as you move around, the hexagon changes. But so the second step in the proof, I'm now going to show you the 70 ways to get from the top to the bottom. And what the proof does is it eliminates 60 of the 70 ways using cross ratio arguments. And then once I have just the 10 ways, I just observe that you really only need 6 at a time. And then I use this cut locus argument to get to the one skeleton of the triangulation. So I'm going to show you the 70 ways, and then I'm going to talk about how they're ruled out. So this program is, I just made some auxiliary studies for this. Maybe it's here, sorry. Okay, so here's one of the ways. This is, I love this way. This is one of these 10 straightforward ways. And then here's another one of these straightforward ways. I love that one. But then there's this guy, and this guy, and this guy, and this guy. There's modulo dihedral symmetry. There's these 7 ways. And then one of them I like. And the other ones actually do appear. So, so it's not like you can say, well, it's just the 10 I like that determine the distance minimizing geodesics. But the saving grace is, what I do is I pretend, it's a funny proof. I pretend that the decagon is I just define a new dynamical system based on the decagon. And then I just analyze the entire map based on that, and I get the final answer. And then I show that for the points, for the farthest points that occur just for the decagon, one of the paths I like is the best. let me put it another way. The other 60, they don't work for any point that counts. Like if a point is sufficiently far away from the opposite point, the one of the 10 is the best. So what I do is I take the algebraic formulas that I found just using the decagon, and I want to show that the distance minimizing points, the distance minimizing paths for those points are realized by the 10 I like. So in other words, I'm ruling out the other 60 where it counts. And this part of the argument is where it's one of the places where I'm using co-circularity. So here I've got Z1, Z2, Z3 are supposed to be 3 of the points of my decagon. And W is an intruder. It's a point I would get by developing out one of these other 60 paths. And P is going to be a vertex of the Voronoi decomposition for the decagon. And all I need to prove is that P is really, like if P is equidistant from these 3, these are the 3 that determine the vertex, that W is worse, that P is further away from W. So in other words, for the points I care about, the 10 paths I like are the best. And for any given point, I can just compute everything and check that it works. But I'm trying to show an inequality like this: the distance from P to W is greater than the distance from P to each of these decagon vertices. And this happens when the imaginary part of the correctly chosen cross ratio is positive. The main point, you'll remember, is like if 4 points are co-circular, their cross ratio is real. So the points inside and the outside correspond to imaginary parts being positive and negative. And if you take the convention right, then the outside is positive. So what I have is, think about it. I've got like 10 choose 3 points I've got to worry about, and then 60 other intruders, and that's 60 times 10 choose 3. And I've got to show that a bunch of polynomials, well, rational functions, but then you take the numerator, I've got to show that a bunch of polynomials are positive on, say, like one of these red triangles in the face, or positive on the pentagon, or something like that. So what I'm going to explain, well, maybe I'll just say this, and then I'm going to move to the last section of the talk, which is algebra. Once I narrow it down to just this hexagon cut locus picture, I still have to prove, I have to figure out which vertices are best. And so there's a competition between vertices, and I want to show that various distances are bigger than other ones. And again, if a distance I dislike ever equals one I like, it comes down to 4 points being co-circular. And so I'm just trying to show that various cross ratio functions are positive on various domains. So everything just comes down to computing a bunch of cross ratio functions, which are, they're numerous. You take this complicated expression and then you want to show that it's positive on some domain. And so what I'm going to explain in the last 10 minutes of the talk is a positivity criterion. Like, you've got a polynomial on a triangle. How do you show it's positive or non-negative? I'm going to talk about positivity, but I really want non-negativity. But so there's many algorithms for this. In one dimension, probably the most famous is called Sturm sequences. There's sums of squares criteria. There's something called the Handelman decomposition. I'm going to talk about one which I think I invented myself, which I love it because it works in every dimension and it's very easy to implement. So I call it positive dominance. So what I'm going to do the rest of the talk, if you don't care about how I verify that these polynomials are positive, you can just check out now because the geometry is done. I'm just going to be talking about algebra and compute what the computer does. But I want to advertise this method. It's really great. If you want to show a polynomial in several variables is positive on a domain, consider using this. So first, the one variable case. I have a one variable polynomial with real coefficients, and I want to know if it's positive on the unit interval. So one criterion is pretty stupid. If all the coefficients are positive, it's positive. But here's a more flexible thing. What I do is I sum the coefficients like this. I take the first one, then I add the first two, then the first three, etc. And then the lemma is that if all of these capital A's are positive, the polynomial is itself positive. And the proof is that I just replace A0 by A0 times X. And since this first one is positive, that decreases the value. But then this new polynomial is just X times another polynomial of lower degree, which satisfies the hypotheses of the lemma. So just by some algebraic trick and induction on the degree, you have this criterion. This is a medium strength criterion. It's not bad, it's not great. And so I'm going to beef it up later, but it's medium. And I'm going to explain how to generalize it. So in higher dimensions, in 2 dimensions, you take your polynomial and you write it out in an array in this coefficient. You write out the coefficients in an array. And then I take all the rooted rectangular sums. Like I just draw a rectangle starting at the top left, and I enclose some of the coefficients and I sum up all the coefficients. And if all the rooted rectangular sums are positive, then again, the polynomial is positive on the unit square. And the proof, it's sort of induction on the number of variables. You treat the polynomial ring in n variables as a ring of polynomials over the polynomial ring in a ring of n-1 variables. And you just apply this criterion inductively. So I'm not going to, the proof is written in the preprint and other places. But anyway, what's nice about this criterion is that it generalizes to n dimensions quite readily. But again, it's not great. So now I'm going to show you how to beef it up. Here's a polynomial right here. And it fails the criterion because 3 minus 4 is negative. But if I look at x over 2, it does satisfy the criterion. And if I look at p of 1 minus x over 2, it also satisfies the criterion. And because p of x over 2 satisfies the criterion, the polynomial is positive on the left half of the unit interval from 0 to 1/2. And this one will say it's positive from 1/2 to 1. So what I've done is I've subdivided the interval and I've applied the criterion. And you can imagine if either of these fails, you can iterate this. And in fact, for strict positivity, this suggests a divide and conquer algorithm, a kind of depth first search through the tree of dyadic intervals. And you halt whenever you can verify positivity using this criterion. And this is if and only if. So this algorithm halts if and only if this function is positive on the unit interval. If you want non-negativity, the algorithm can fail. But anyway, if the algorithm halts, you've succeeded. And the nice thing about this is this algorithm also generalizes to higher dimensions. If you want to do this on the unit square, you can divide it into 4 and just make a change of variables and test the positivity criterion on each of the pieces. And if that fails, you do it again. So in general, there's a kind of a depth first search through the kind of tree of dyadic cubes that will halt if and only if the function's positive, and then often halts when it's non-negative. So, okay, but the last thing I want to say is a square has got nothing to do with the kind of shapes we see in the pentagon. I mean, we're interested in, regions like this, which are quadrilaterals or triangles or whatnot. And so I never deal with these curvilinear things. I always approximate by triangular regions. So I just want to explain very briefly, like, there's this little technology that I've been telling you about, this algebraic technology for proving that a polynomial is positive on the unit square, but I want to apply it to triangles. So what do? Here's an example. If you look at this map, this is a polynomial map that goes from the unit square to a triangle. It maps this white square to this white triangle. And if I have some polynomial p that I want to know is positive on the triangle, I just have to show that p composed with f is positive on the unit square. So, and if I have some other kind of triangle, I just can apply, again, composed with an affine transformation. So using this map and affine transformations, I can reduce all questions about positivity to this divide and conquer algorithm. And then, well, that's pretty much the end of it. I just, I don't have, well, just to say it simply, I take my 500 or so polynomials, which are really quite big, and I just feed it into the computer, and then it just says yes for every question I want to know. So it just, but look, to be fair, I also computed it numerically. I didn't just, I really did the numerics first to make sure it was right. So just maybe to summarize this whole thing, the first step is a sort of a computer-assisted proof plus cut and paste geometry. And then the next two steps are just a big computer program which shows that a bunch of cross ratio functions are positive or non-negative on the relevant domains. And then this is all interpreted in terms of the Voronoi decompositions and co-circularity, and then that proves the result. So anyway, that's maybe I'll just show one more thing. I still have a few minutes. I'll just show off the program. It's downloadable from my website, and it also has maybe I'll show this just to encourage people. You can actually use this thing. It's got text you can read, and it's sort of like a paper. You can push a button and it will tell you what each of the things does. So it's sort of like a well-documented program. And here, somehow it's got the Voronoi decomposition superimposed over the graph, and you can sort of make things more or less transparent to sort of see things better. And anyway, so I would say, like, I was kind of disappointed that this paper turned out to be so long. I thought this was going to be just a walk in the park, an easy proof. But you can use the program and sort of see exactly what the map is doing. So that's it.
Well, thank you. Thank you very much. It's very impressive.
Thanks.
Does it help to know that isn't the shortest distance or the furthest distance from a vertex is the opposite vertex?
That's true. Yeah, that's certainly true. I mean, that's good to know. I mean,
so if you look at the opposite faces near that vertex, okay, the shortest distance is in the opposite vertex, but it's very close to.
Yeah, probably. That's right. But then you have three choices for where it could be. I mean,
right.
It could be, and there's like, I forget how many viable ways there are to get there. like, 100 or something. I mean, there's many sort of, I don't know, I don't know, there's lots of ways to do it. And then you just have to, but yeah, you're absolutely right. I mean, I think like yeah, I noticed, so I did this is a kind of a curiosity. I computed the distance, from the vertex to the opposite vertex in the intrinsic metric. And it's 4 3/4 up to something like 3 decimal places or something, like it's almost 4 3/4, like up to some high precision. It's kind of weird. Anyway, but you're right. I mean, for the vertices, it's clear what it is. But somehow it's this map, in general, it's this map, which is just like one step up from a projective transformation, some kind of bi-quadratic foliated projective map.
So, so what's the point that has the furthest distance? Is that between the vertices?
The furthest, it's funny. I didn't, yeah, probably. I mean, I didn't actually, one thing this result says is that at least to figure out the answer, you just have to look at the one skeleton of this tiling, because this map, increases as you iterate the map, it increases the distance. So because everything is attracted to this graph, the answer has to be in the graph. And then, yeah, I mean, I didn't actually, for the octahedron, it's true. The farthest one is but I didn't, I think it's true. I didn't, it's funny. Maybe I didn't actually work this out. I imagine this is known, but I didn't, I guess I would bet yes, but to be honest, I didn't actually do it.
So things are attracted to that graph.
Yeah, that's right. Things are attracted to that
it's
graph.
Never after a finite number of steps. Is that right?
That's right. And it's really, I find it really beautiful because this map, on each segment, you can think of the segment equipped with the Hilbert metric, which is just the metric which makes it the hyperbolic line. And then, the cross ratio of the relevant points will tell you the translation distance in this intrinsic hyperbolic metric. And you have a pencil of lines and a one parameter family of, and the cross ratio is a holomorphic function. It's actually, it sort of achieves all values. And what it means is that this kind of Hilbert translation length is changing on different segments. And in fact, it goes to 0 when you go into the corner. So it's like points are going towards the edge extremely slowly as you go towards the edge, because this translation distance is going to 0. So like knowing this explicit formula really tells you this interesting geometric fact that somehow, if you looked at the image of like a straight line under the map, it would develop a cusp out near the corner. So it's sort of an interesting, you can see you can sort of use the hyperbolic geometry of this map to get some Euclidean information about, what it does globally, something. Yeah.
I don't mean to hog. Are there any other people with questions or comments?
I just have an easy question, I think, which
Sure.
is, I'm really interested in this, your method of positive dominance for these, to do this. What's the best place to read about that?
I mean, I've written, somehow I keep using it over and over again. So like one paper I wrote was called Lengthening a Tetrahedron. And this is in geometry. I can put this in the chat. One place is, so that's one place. Another place is so those are two places. I mean, basically, I've used it a bunch of times. I mean, and I have a feeling that some like computational algebra, they must know this. Like I'm just not in the right circles. I mean, I've never found it in print, and but it's really great. I mean, I've used it a bunch of times, and I mean, one of my students used it and he thought it was great too. So, I mean, it really, you can, implement it. And I mean, in one dimension, this thing called Sturm sequences is it's much stronger. It will tell you the number of roots. And it's pretty neat. Like you take the polynomial and its derivative and you do the Euclidean algorithm and you get a bunch of polynomials, you evaluate them at the endpoints, you get two sequences of numbers, you look at the number of sign changes, and that's the number of roots. It's beautiful, but and then there are like some generalizations of this Sturm sequences to higher dimensions, but I it's sort of pretty complicated. And then there's like, yeah, like sums of, you try to write your function as like a sum of squares. That's another popular method. And I mean, if you get lucky, you can do this. And there's some beautiful things. The Handelman decomposition is another.
Definitely been stymied on many things where I'm trying to find positivity of, 6, 8 variables, lots of variables. Usually.
Yeah, right. No, that's right.
Problem.
Yeah, I mean, this thing, it works, you might just get lucky and find that like after a couple subdivisions, you're done. But like, I mean, I used it to analyze the dynamics of some birational map in the plane. And I had to do like thousands of iterates and stuff. I mean, you have to subdivide quite finely to actually show this kind of thing.
I guess if your polynomial actually has zeros,
you're done. It doesn't work. Yeah, for example, another example is like, like if your polynomial, like I mean, if you're lucky and the zeros are sort of like on the cracks of the subdivision, you could do it. But like imagine the zero set was like a parabola or something like this. I mean, then this method is done and won't work.
Right. I mean, in principle, you can do it with Tarski elimination.
Yeah. That's true. There is, I should say that there's this, what is this called? Like cylindrical, I forget what this is called.
Cylindrical algebraic decomposition.
Yeah. There's some, I mean, right. You can, if you want to know, like if like a semi-algebraic set is empty, there's an algorithm or something, but.
It's doubly exponential.
Yeah, it's bad. I mean, it's bad. But like, so it's a little bit of a funny problem. Like, I mean, I've run into these things too with like energy minimization problems where like things like Thomson's electron problem, where like it's just saying some function is positive, and you can even reduce it to algebraic functions if you're careful. But I mean, it's too complex for that. But you're right. There's other. I don't know why I like this. It's just firstly, it just often works, and it's very easy to implement. Like just a page of Mathematica code will sum up the coefficients and test if they're positive. And so, yeah.
Simplicity is good.
Yeah. That's right.
You can think you've proved something numerically, but actually you had a bug in the code because your method was too complicated to program correctly.
Yeah, that's right. I mean, it is true. I mean, you have to, well, there's always that problem. I mean, probably, I don't know what you can do. You can try to do the calculation several ways, or of course have other people do them.
You could do it in a proof engine.
Yeah, sure. You could, although I don't think a proof engine would really, if the proof engine is more like for like what is this, Isabella or the lean machine.
You could probably do your proof in lean.
Yeah, but you could do what I mean is like lean, I think it's just about formal mathematics. It's not necessarily about computation.
Right,
you know what I mean? Like
you use your positive dominance method to produce the lean program that is then checked by lean.
Oh, that's interesting. Yeah, that's a good point. I mean, it would produce a partition and then it could just check it or something. That's a good point. Although, I mean, it's somehow it's an interesting philosophical question. Yeah, I'm interested in this. Like, I get the feeling like that. I mean, for these kinds of calculations, they're not that deep in a way. Like what I mean is like you're just sort of doing this one thing over and over again. But like, so I'm not. It's a sort of a short program, so like it's not too hard to check that, and then you're just pushing the button. Like maybe lean is better for like these really complicated logical arguments. I think also, but maybe both. I don't know. I mean, I feel like I should learn lean at some point. Like, I mean, more and more people I know are, using this thing for, even in geometry. I mean, people are, doing things. I mean, but yeah, at the moment, I mean, it's more, yeah, but I don't know. Yeah, like if you proved a paper, suppose you prove something in lean, and it's a really great result, you send it to the annals or something like, and you say, do they just say like, okay, you checked it in lean? I mean, like you have to write all this computer code to check it. You might screw up in lean. You might have the wrong, you know what I mean? Like you might, I mean, can't you sort of screw up in lean? You think you're really proving it, but you.
I mean, you could define something that isn't what you think you've defined, and then prove theorems about the thing you.
Yeah, I guess that's right.
Defined instead of the thing you think you defined.
Yeah. So, but anyway, it's something I may. Who knows? I mean.
Yeah. Anyway, the graphics are already pretty too. So.
Oh, thanks.
Congratulations on that.
Very nice.
Yeah, it was in Java. Anyway, it was all Java, programming in Java.
Have you done this sort of thing with other, say, symmetric polyhedra, not necessarily?
You mean like Archimedean solids or something like that?
Pardon me?
Like Archimedean solids or one?
Yeah, something like that. It still has a lot of symmetry.
Like the soccer ball or something. No, I mean, somehow I did it for the octahedron because, my friend Peter Doyle got me interested in this problem and I just thought I could do it and did it. And then I was giving talks about it fairly recently. And then someone said, well, what about the dodecahedron?
Yeah,
so
right.
then I did that. And, I wasn't expecting it to be, I think the problem is that like the regular pentagon doesn't tile the plane.
Yeah.
So that somehow for the octahedron, it's like you have a kind of a global tiling, which, lets you simplify things a lot and organize all the paths. But so some of these other ones probably don't develop out into tilings either, like the soccer ball or something.
Yeah, but the icosahedron is sort of almost the same as the dodecahedron.
Yeah, well,
but
right.
It is regular triangles.
No, that's true. No, that's true. It is funny. Yeah, people have, I suppose like duality, like maybe it depends on the problem. Like, you know what I mean? Like the, so like something is true for one thing, it might not be true for the, it's dual, like something might be much harder for its dual than for the original thing for some reason.
Yeah.
But I think maybe I'm just talking out my hat, but I mean, duality seems like really a three-dimensional thing, for the polyhedra, like, and this is all about this intrinsic metric or something. You know what I mean? So maybe somehow duality is not as important or something. Yeah.
You said that irregular tetrahedra have been done.
That was
they don't develop as well.
This guy, he's a student at Cambridge. He's a. I gave a talk on the octahedron fairly recently for the math club at Cambridge, and then he got interested in, I said, he asked me about the tetrahedron, and I said, well, I don't know in general if it's done, but he worked it out, and I said, you should write this up and publish it. It's great. And then he said, well, I've got my exams coming up. I have to do something else. But maybe if somebody, I don't know what he did with this. It was very, I don't know how rigorously he did it. He kind of just discovered the answer. But it's really neat. I mean, he really looks at the parameter space of tetrahedra, and he says he divides it into zones. He says you have this behavior here, and it's all pretty similar to this kind of map I was getting is it appears sort of in all of them. It's just maybe it's the most beautiful pattern in the dodecahedron. But
what happens if you take a triangulated convex polytope that's generic? Is there anything you can say?
I don't know. I mean, my student Zili Wang, she looked at centrally symmetric octahedra where all of the cone angles are equal. So I liked this family because they they sort of are the ones that come up in a paper of Thurston's about shapes of polyhedra.
Hmm.
So this, you would think like, this is a really nice family. What does it look like? And it was a mess. I mean, it was kind of a mess. Like there was still this kind of seemed to be this kind of one-dimensional attracting set, but
Oh, I see.
it wasn't linear. And then there was like the discontinuity set, which was also sort of a mess. I mean, I don't know if she like was completely systematic. Like it's possible there were more general things you could say that were neater, but so she wrote a paper about this, and she published it in Geometry Dodecahedron like in the last 3 or 4 years. Zili Wang. And
Have you tried the right-angled hyperbolic dodecahedron?
no, I mean, like this is something I really just finished like 2 weeks ago.
Oh.
So like I really was.
That would be nice because the developing map it does have a tiling.
No, that's true. That's interesting. Yeah, that's a good idea. I mean, I wanted to look at things like the congruent surfaces. So like the hyperbolic plane mod, the set of integer matrices congruent to 0 or to identity mod P. Those are sort of like generalized platonic
Right,
solids.
or like 2, 3, 5 triangles.
Yeah, something like that. So I thought somehow
2, 3, 7
I wondered about that. I thought it would be really neat to work out what this thing looks like for all of those. Like, because certainly the picture is just restricted to one triangle. So, I guessed it might be similar, but I don't really
And
know.
there are icosahedra where all the faces are congruent too, right? I don't know if that.
Yeah, sure. Yeah.
I don't know if
I
that
mean,
helps.
the icosahedron, I mean, somehow I didn't work it out, but I convinced myself that the answer looked very much like the octahedron.
Oh, I see.
So yeah, it's pretty similar because, I mean, but I didn't write it down, but